When the universe was a newborn, the laws of physics were very different. It was immensely hot, and during this time, the strong nuclear force separated from the electroweak force, resulting in the creation of three fundamental forces. The separation of forces released a huge amount of energy, causing the universe to expand rapidly. In just a fraction of a second, the universe expanded from the size of an electron to the size of my palm. This phase of rapid expansion is known as cosmic inflation. This theory was first developed in the 1970s and was widely accepted because it was able to solve the horizon problem. But what is the horizon problem? The leftover heat from the inflationary period formed the cosmic microwave background, or the CMB. It is the earliest form of light visible to us. When scientists measured the temperature of the CMB, it came out to be exactly 2.75 Kelvin at every point. And now it's dessert time. Here I have some hot brownies and some ice cream. If I keep the ice cream over the brownie, they eventually attain the same temperature. Now imagine that I want to share this dessert with my friend who has the brownies and I have the ice cream. The problem here is that I have to transport this ice cream to the other endpoint of the CMB, about 93 billion light years away. Even if I travel at the speed of light, the time it will take for me to reach my friends exceeds the age of the universe itself. But observations show that my friends do have the full dessert. How is this possible? The answer is cosmic inflation. If we reverse time back to the era before inflation, we see that the universe was very small in size and was composed of both hot stuff and cold stuff. The stuff had enough time to interact with each other and attain a uniform temperature. Then inflation took over, making the uniform patch of space stretch exponentially, forming the uniform universe we see today. And the horizon problem was solved. Post inflation, the universe started to cool down and some of the oldest stars were formed. Due to the clumping of matter in one spot, it was expected that the expansion rate of the universe would slow down because of the immense gravity. In 1994, a group of astronomers devised an experiment to find the rate at which the universe was slowing down. But in 1997, they concluded that the universe is accelerating. This acceleration was later attributed to dark energy. So, what does dark energy do to make the universe accelerate? The answer is repulsive gravity. Dark energy exerts a gravitational force which is repulsive in nature, and since our universe is made up of 70% dark energy, it makes the universe accelerate. Imagine this piece of cloth being stretched. In this case, V act as dark energy, causing the cloth or space to stretch, and the interatomic forces of this cloth act as matter, trying to resist this stretch. Someday, it might become strong enough to dominate over interatomic forces, making individual atoms rip apart. But we have about 2.5 billion years before worrying about that.